How will you speak to that? What does the fox say? What the fox say? What the fox say? What the fox say? What does the fox say? The secret of the fox. Dog goes woof, cat goes meow, bird goes tweet, and mouse goes squeak. Cow goes moo, and frog goes croak, and the elephant goes toot. Ducks say quack, and fish go blub, and the seal goes ow, ow, ow. But there's one sound that no one knows. What does the fox say? What the fox say? What the fox say? Hatty, hatty, hatty ho, hatty, hatty, hatty ho, hatty, hatty, hatty ho. What the fox say? What the fox say? Big blue eyes, pointy nose, chasing mice and digging holes. Tiny paws up the hill. Suddenly you're standing still. Your fur is red, so beautiful, like an angel in disguise. But if you meet a friendly horse, will you communicate by more? How will you speak to that? What does the fox say? What the fox say? What the fox say? What the fox say? What does the fox say? The secret of the fox, ancient mystery, somewhere deep in the woods. I know you're hiding. What is your sound? Will we ever know? Will always be a mystery. What do you say? You're my guardian angel, hiding in the woods. What is your
Baby,
Dog goes woof, cat goes meow, bird goes tweet, and mouse goes squeak. Cow goes moo, frog goes croak, and the elephant goes toot. Ducks say quack, and fish go blub, and the seal goes ow, ow, ow. But there's one sound that no one knows. What does the fox say? What the fox say? What the fox say? Hatty, hatty, hat, ho. Hatty, hatty, hat, ho. Hatty, hatty, hat, ho. What the fox say? What the fox say? Big blue eyes, pointy nose, chasing mice and digging holes. Tiny paws up the hill. Suddenly you're standing still. Your fur is red, so beautiful, like an angel in disguise. But if you meet a friendly horse, will you communicate by more? How will you speak to that horse? What does the fox say? What the fox say? What the fox say? What the fox say? What does the fox say? The secret of the fox, ancient mystery, somewhere deep in the woods. I know you're hiding. What is your sound? Will we ever know? Will always be a mystery. What do you say? You're my guardian angel, hiding in the woods. What is your
Good afternoon. Welcome back to EECS120A. So today we are going to continue our discussion on data path components and their interplaying with sequential circuits. But before we start, there are always things that we want to remind you. And well, you probably also noticed that, well, the song we played today is What the Fox Say. And we have a pretty good student called Fox. And I feel like in the last lecture, the pattern is like, oh, okay, whenever the professor asks a question and let's see what the fox say, right? So, but you know, this is the class for everyone. And the material that we start teaching after the midterm is surprisingly important, and they will be accounting for a majority part of your final. So if you don't try to and another thing which you will be stunning is that many things that we have talked about in class is actually not, it's only a very brief paragraph in your textbook, which is not explained well and not having too many examples for you to work with. So if you didn't pay attention to the lecture, and it's very hard for you to nail the final. And a lot of you are working a lot on the lab, but thinking about that, we are dropping one lab from your class, from your final grade. So each lab is essentially just like 6 credits, 6% of your final credits, and one of them is going to be dropped. So if you already have 5 in 100, technically you can drop the last one because it doesn't count at all, right? But for final, that's actually the most expensive part in your grading, because it's 25%. One final is 25% and includes everything and a lot of stuff that we mentioned only in class, only in the lecture. So please pay attention to the lecture, and if you have questions that you don't understand how to deal with that, try to address that during the lecture time. Otherwise, it's really hard to retroactively figure out what's going on there. So please pay attention to the lectures. So before we start, I start to feel like, yeah, because this is close to the end of the quarter, so a lot of stuff that you are probably messing them around. So it's always important to remind you guys where we are. So we previously we mentioned that the processor is the computer system has a memory hierarchy in a way that the processor core has registers, and those registers are directly interact with your LU components. For example, like the adder, the multiplier that we are going to talk about today, and also because registers can only provide limited amount of data storage, and DRAM is way too slow. So we put SRAM caches in between the registers and DRAM. However, no matter registers, SRAM, DRAM, they are all volatile memory, meaning that if you plug your computer, then everything is going to be gone. So we want to, if we want to store things persistently, we should use a non-volatile memory like flash memory, which we have talked about their abnormally behavior, like the program erase cycles are very limited. Okay, Fang Zong, questions?
Yeah, I want to ask you about the things about the material that you said. You said that a lot of the material you're covering in a lecture isn't fully covered in the textbook or whatever.
Yes, but like this part is not in there.
But we're still going to be tested by
for sure. For sure. Otherwise, why am I teaching those?
Well, I just because, well, I think that other students that takes 120A doesn't get covered or doesn't get taught by this material and get tested by the other stuff. I feel like maybe we should.
No. Well, I mean, every professor is teaching differently, and not even every professor is using the same textbook. Like a lot of students are using the last version of the textbook, and a lot of the material that's covered by this class is actually you can find them on the last version of the textbook. And the reason why I have to cover a lot of stuff through only the lecture is because they are not in this version of a textbook. And we get this version of a textbook for free. And the paper version it's surprisingly expensive on Amazon. It's $200. And it's an earlier version. So that's why we have to cover a lot of stuff that's not in the current version of the textbook, but they are very important. And I mean, the textbook is only covering you the very, very basic stuff. And the most important thing about education is that we want to prepare you better for your future. And those are the stuff that I teach you in a class are the stuff that you must know. It's not about if the textbook cover it or not. It's because everyone expects a student who took logic design before must know these things.
Okay.
Is that okay?
Yeah. Thank you. That answers the question.
Okay. All right. So so flash memory, as you can see, like their program erase cycles are very limited, and as the technology evolved, and you can see the program erase cycles are even more limited. So because the flash memory, they have this characteristic. So when you design your programs, you must be super careful about the underlying hardware components. The underlying hardware components, they have their own characteristics. And if you are not aware of that, like the example that we have shown before, like the floating point adders, like if you don't know that the floating point adders has such limitations, then there is no way that you can get your program functioning correctly. All right. So the last lecture, we have some question on the clock signal. But however, I don't feel like the class is doing great in solving those frequency clock related questions. So let's have a small recap on this. So before the midterm, we have the concept of a clock signal, that the clock signal is controlling the sequential circuits in a way that you know that the clock signal drive the flip-flop operations. And when the flip-flop receive the clock signal, it will receive, or it will get what currently in its input and output what's currently inside their cells. So this is the basic idea of how clock signal will control the whole execution of the sequential circuit. However, after your flip-flop outputs those values that you store in the cells, you also need to know you also need to give the circuit sufficient amount of time to finish their work in combinational logic, so that before the next clock signal, you can propagate the right result to the flip-flop for maintaining their states again. So the clock period look like the red part. Read the red part of the slide. Must be longer than the longest delay from the state register's output to the state register's input, known as the critical path. So look at this serial adder, right, that we discussed in the last lecture. So we have a combinational circuit part, which is the full adder, and we have this one as the register, or say the flip-flop, right? So and through what we have learned before is that if we want to realize this serial adder, this is the circuit that will be used, right? So now I have a question for you. Okay, so now I have a question. Well, looks like I didn't make the animation very well. So the question here is that what's the critical path of the circuit? And as you can see, the critical path of the circuit is actually D, but can you tell me why this critical path, the D critical, is the longest, and how much time it would take? Well, the answer is actually 5 nanoseconds, right? So, so the critical path of the circuit is D, because if you look at that, so first of all, each gate delay is 1 nanosecond, and the delay in register is 2 nanoseconds. So if you go through the path A, which only goes through 2 gates, so the delay would be 1 plus 1 is only 2 nanoseconds. And for B is also 1 plus 1 is 2 nanoseconds. And for C is 1 plus 1 plus 2, that will be 4 nanoseconds. But for phi, that's going to be 1 plus 1 plus, let me see, I think, oh yeah, so this one is also long enough to give you the input. So this one is also like 4 nanoseconds, right? So we know that the cycle time that will be determined by this serial adder will be 4 nanoseconds, right? So so if you go and this is either C or D, they are the longest paths. They require 4 nanoseconds to well, so okay, let me see. So for the C, it doesn't include the flip-flop part, so it's only 2 nanoseconds, right? So, but for D, it only it also include the input and the output. So it's the true circle between the clock flip-flop. So it's the critical path. So the critical path of the circuit is actually D, and the total amount of time that needs is actually 4 nanoseconds, right? So that's how you decide the critical path and the cycle time of your circuit. And if you know the cycle time of your circuit, right, then 1 divided by your cycle time is actually the frequency. So you can get this table of frequency. Oh, by the way, this stuff is also on your textbook, but your textbook only have a very one short paragraph, and they don't even explain to you what's going on there. So if you just read the textbook, I highly suspect that you understand what the textbook is talking about. So these are the stuff that are really important that you have to pay attention to the lecture, even though the textbook only give you very brief description on that. But you are not everyone get an EE degree or a CS degree who took logic design. These are the must know stuff, even though the textbook only spent very short paragraph in talking about that, because the reason why they put this short paragraph, because they think it's easy. But apparently through our Q&A questions, we are suffering at this part. So that's why we spend so much time in explaining this. We give you so many examples on this. Those examples are not even on the textbook, because the textbook is just not giving you sufficient amount of information to get you a full picture about what's going on in your digital design. So that's why we have to have that, and we have to get that tested. Okay, so knowing the cycle time just give you the frequency. And through that, another thing that we are curious about is that how to estimate the area and delay of adders. And this is using the stuff that you have before the final, before the midterm. You know that, well, for 32-bit serial adders, I only need to with 4-bit COA, it's definitely smaller than the 32-bit COA. However, the amount of cycle is smaller according to what you learned before. So it's a very good trade-off between 2 and 3. However, if you look at, what you really want is to save your space, then 32-bit serial adders becomes the best choice, because you only need one copy of the adder, and you can get you can get the same function. Another thing that you should learn so far is that, well, if you check the frequency that we have, right? Usually you would correlate frequency with the delay. Like the shorter the frequency, the lower the delay, end-to-end delay of finishing one thing. However, 32-bit serial adders, they are actually giving you the longest end-to-end delay. However, the frequency is the highest. So one thing that you should learn is that frequency is not necessarily correlated to the end-to-end latency. So today we are going to talk about a technique, a mechanism that would make that would make more correlation between frequency and your performance, or say end-to-end delay of a larger amount of things. That technique is called pipelining. And then we are going to talk about multipliers, which is also something that we should talk before the midterm. However, because we don't have sufficient amount of time, we haven't get a chance to talk about multipliers. But in the meantime, since we learn sequential circuit, let's see how multipliers and sequential circuits they can work together. So the concept of pipelining is this: we have different parts of the hardware works on different requests or commands simultaneously. And a clock signal will control and synchronize the beginning and the end of each part of the circuit or each stage of the work. And because every cycle, instead of accomplishing the complete task, you are right now only finishing part of the job. So you need something to store the intermediate result. That's called pipeline register. So the pipeline register between different parts of the hardware will help to keep those intermediate results necessarily for the upcoming work, which is helping you complete the rest. And register, it's pipeline register, but it's basically a register, an array of flip-flops, which you have learned before. So let's look at this graphical representation of pipelining. So the basic idea of pipelining is that we have a clock that's shared by all the hardware components. And you have pipeline registers like those yellow ones. And let's say I connect those pipeline registers and control my circuits with the same clock. And then during every clock cycle, I only perform part of the job. So let's say right now I have a job. The clock signal comes, I have a job, which is colored in red. And during the cycle time, it only goes through the first stage. And then the next cycle, clock cycle comes. The red one will be propagated to its next stage. And the first part of the circuit can be freed up to the next job. And similarly, when the third clock signal comes, the first job will move to its third part, and the second job can move to its second part, and the third job can go to the first part. So you can see at this moment, three of the hardware components within our hardware are working on three different things. And go to the next clock cycle, four of them are working on four different things. Next clock cycle, five of them are working on five different things. So this is the concept of pipelining. So let's use the concept of pipelining for the 4-bit serial adder. So remember, serial adder, we only generate 1-bit outcome per cycle. So if I want to make it a 4-bit adder, I need 4 cycles for that. So the pipeline 4-bit serial adder would be like this. I have 4 different parts of the circuit, and the first part of the circuit is going to add the first bit, and then the second bit, the third bit, and the fourth bit. And whenever the first one is free, it's okay to receive another job. So that's the basic concept of pipeline serial adder. So let's look at this. So if I have this amount of job to do, and in the very first cycle, when I receive this red task, the first cycle, I am going to work on the first bit outcome of the first add. And then the second cycle, I'm working on the second add and the first add for the second add operation. And if you keep going, the third cycle, you can see we are right now executing 3 adds in parallel. However, the first add is doing its third bit. The second add is doing its second bit. And the third add is doing its first bit. Now, the fourth cycle, as you can see, the first add is right now processing its fourth bit of the outcome, and the second add is right now entering its third bit processing, and for the third add, which is the green one, is right now just doing its second. And because the green add is right now not using the first one, so the first one is yelled to the blue one. And let's keep going in a fifth cycle, because the red add is now finishing all its 4 bits. So we can free up that circuit and it's already done. We can output the result. But in the meantime, the orange add is now entering the 4th bit addition. And for the green one, it's doing the third. The blue one, navy blue one, is doing the second, and the purple one is doing the first. In the next cycle, as you can see, we output the orange again, get rid of that, and 4 other adds are doing in parallel. And if you keep going, you can find out at some point we are always completing an operation each cycle. So that's the basic concept of the pipeline adder. So right now, you can see with the pipeline adder, the cycles per add operation on average, if you have sufficient amount of them, will be just 1. So I have a question for you. If I have if I have 10 millions of ads, which of the following pipeline which of the following pipeline adders would be the most would give us the best shortest amount of time to accomplish those tasks? Okay, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so let's see. So the most popular answer is C, but it is also popular. So can I have some of you telling me what you guys are thinking and why you why you advocate for your answer? Raise your hand, raise your hand. Raise your hand. Why you pick C? Why you pick E? I want to know that. I mean, the more, if you express your idea, it will definitely help you in a final. Because in a final exam, I think our multiple choice question would be asked a little bit differently, in a way that we are not just asking you about what's the right answer, but we also need you to explain. So if you can have some of you to come up, speak up, then you know what kind of answers that we are expecting to see. Still nobody? Come on, tell me what do you think? Okay, I have Shilo.
Well,
What do you think?
I personally pick E
You
because
pick E
if
because
it's assuming the gate delay of it, and
mm-hmm,
first of all, for to the carrier ripple adder, that
mm-hmm.
generally has the worst gate delay. And by process of elimination, I eliminated all the answers I didn't have to as the worst one.
Mm-hmm. Okay, so let's see, like for pipelined for so let's go back and see this one, right? So for the pipelining, right? The pipelining basically try to help us. One thing is that right now with pipelining, uh, every cycle you are outputting an add operation, right? So in this way, um, what factor would determine how many add operation that you can accomplish within a given period of time? What is that?
It should be the critical path, right?
The critical path of what?
Of the worst possible outcome. So in the cases of the serial adders, for example,
Mm-hmm.
those depend on the registers, and the registers already hold a value. But with the ripple carrier adder, you have to.
Okay, so if you go back to what we have here, right? Is the critical path only the register?
No, there's also two gates there too.
Right. So here's the thing, right? The critical path is this, right? So and actually it's not well the correct term here is actually the cycle time, right? Because you are essentially like outputting one instruction per cycle, right? So it's actually the cycle time, and the reason why you said it's a critical path because the critical path of your circuit decides the cycle time, right? So it's actually the cycle time determines your how long is it on average for you to accomplish an instruction, right? And if you go back, if you go back, if you go back to if you go back to this, if you go back to this, right? Which adder here is giving you the best frequency or say the highest frequency?
That'd be number 4, right?
Yeah, that will be 4, right? And the second one will be the third, and then the first, and then the second, right? So it's exactly the same with the pipeline result, right? So what pipeline basically doing is that, well, we make each cycle outputting an instruction. So the average latency of finishing an add operation would be equivalent, almost equivalent to the cycle time of your circuit. So in this way, and thanks for your opinion. So in this way, you can see that with pipelining, we are correlating the cycle time of your circuit to the end-to-end latency of finishing a lot of jobs, right? So if you just have one add, if you just have one add, then the carry look ahead adder would give you the best performance. However, if you have 10 million adds, then the pipeline adder would give you better performance than that. So this is the basic idea of, but this is how pipeline would help improving the end-to-end latency of a bunch of jobs. So if you look at that, right now you may be confused. Well, there are so many matrices, right? So we talk about latency. So the latency usually we mean is the amount of time to finish an operation. So you can say like access time, response time. So when you click the mouse, how much time it takes for you to receive the outcome, that's called latency. That's called latency. That's also the response time. Or say like, okay, if I start watching a movie, when can I start seeing a friend? The first friend, that's the latency, right? And the throughput is the amount of work can be done within a given period of time. So saying that if I want to download a file, you are actually receiving not just one frame, but a whole file, right? How much time it takes to download a whole file. And on average, how much time to receive per a megabyte or gigabyte per second. That's called throughput. And if you are familiar with GPUs, they always use like M flops or G flops to represent how capable their GPUs are. That's also using throughput as a matrix. So if you still don't understand this, let me tell you about some analogy about the latency, delay, and throughput. So right now saying that I have a good friend at UC San Diego, and right now everyone is under self-quarantine, and sometimes being a single person like me is very, very boring during night. So what my friend suggests me saying that, okay, so I can drop you off. Well, I have tons of movies that you can grab from me, and I'm super excited. They are 4K videos. So one thing we could do is one thing we could do is that there are two options. First of all is that, well, I can subscribe a super fast network like the right-hand side, which doesn't even exist. And it's called 100 gigabit network. And if you just pay attention to the recent Spectrum network commercial, they are advertising for 200 megabit per second. So this is like, you know, how much faster? About 500 times faster than that, right? So so with that kind of network, right, it's essentially you can get 12.5 gigabyte per second of data. And if I have 2 petabyte of data, it will take about like, you know, 2 days to get this movies, right? And you can start as soon as you receive a friend from those movies, then you can start watching a movie, right? And another option is that you can use a Toyota Prius, right? And it takes about like 100 miles from here to UC San Diego. And if you drive on the highway for 75, which is not an advised speed, then it takes about, I would say like 1 hour, 20 minutes to get there, right? And if you want to make a round trip, it's about like 3.5 hours. So and if you put hard drives into your Prius, then you can get like, you know, around like 3,000 hard drives, and you can get this 2 petabyte of data within just 3.5 hours. And if you calculate this equivalent bandwidth, it's actually around 300 gigabyte per second, right? Versus the very fast network. So the bandwidth of driving a car is actually a lot better than a network. However, before you get back from UC San Diego, you cannot see anything. So the response time is actually worse. So that's an analogy between the difference of latency and throughput, right? Hopefully this would give you a good idea about what's going on there. So latency just means that if I just want to get a small piece down, how much time it takes. And for throughput, it means that if I have a large chunk, if I have a large pile of jobs, which one would give me better performance, right? So that's the difference between these two metrics. Okay, so as logic design, we always care about the cost of manufacturing circuits. So right now, can you look over this? Consider the following adders. Can you rank the number of transistors in implementing each of them? looks like the question is not setting correctly, so let's reuse this one. Sorry. All right, let's wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay, so let's take a look of what you guys think. So looks like we have the most popular answer as B, but E is also popular. So look, so like this question, right? So at least we know, like, there's only one answer and half of you didn't get it right. And if you pay attention to what the question is asking about, and you will surprisingly found that it looks like this is not covered by the textbook, but how to estimate the area, how to estimate the number of gates, and those adders are all within the textbook. So that's the thing, right? So in the final, although I said this is not covered by the textbook, but the textbook only give you concepts. They don't give you a lot of real examples regarding how these things are making into practice. So that's why you have to pay attention to the lecture, because those stuff, this you cannot find in the textbook. Is not exactly the same type of question of the textbook, but all the techniques, all the knowledge, all the concepts are actually taught even before the midterm, right? So, but according to the result that I share with you, right, at least even the most popular answer is only like 30%. So more than half of you didn't know what's going on there. So you have to pay attention to and what other people are thinking about. So right now I'm inviting some students, some of you to share your thoughts with us, and it's okay to be wrong. And I would rather to have you being wrong so that you will remember, oh, what mistake or what kind of misconcept I have. Okay, so after saying this many stuff, still no one want to raise the hand. Come on, don't be shy. I'm not going to bite you, especially I'm far away from you. Okay, I have Nicholas.
Yeah, so the only thing I know is that one's bigger than two, but I'm still kind of confused. How do you estimate the area? Because I know you do it through transistors, but it's hard for me to actually picture what an 8-stage pipeline 32-bit serial adder made with 4-bit CLA adders. Like, I don't know how to like put that together. You know what I mean? I'm just having trouble with this stuff.
Okay, so this is actually a question that we had. Well, so first and the second, that's actually a question we had before the midterm, right? Mm-hmm. So if you dig out the information we have in the past, well, the slides, if you still have, if you know where the slides is, right? It's actually, okay, Fox, do you have anything to say? Hello? Fox? You raise your hand. Do you have anything to share? Hello?
Hello?
Yeah.
Are we still talking about this question? I just
Yeah. Okay.
haven't
So
gotten
do
the
you have
answer yet.
anything to share? Yeah, well, I haven't talked about the answer yet. And Nicholas seems like having some issues with the area and the cost. And actually, I think I can go to one of the slides that I have if you don't mind. Let me see. Well, so if you don't mind, okay, so I think I have, okay, so, right, so regarding how to estimate the number of gates, right? So a number of transistors, right? The only thing that you can do is that you have to see what it looks like in the real circuit, right? So for the full adder, so this is a serial adder, but the full adder is actually like this, right? So if you have a very good estimation on what's going on there, a full adder actually take you about 50 transistors to implement, excluding this part, right? And for a serial adder is actually 50 plus, let's say like a flip-flop requires 18 transistors, right? So this is how you get the number. And for carry lookup-ahead adder, right? We also tried this question before by realize it's carry lookup-ahead logic using this Boolean circuit, and like each, like this is a two gate transistor. This is a 2 input gate, so it would take four transistors, right? And this is also a 2 input gate, so it would take 4 transistors, so it's a total of 8. So using this, I think, Nicholas, do you remember this now?
Yeah, I do remember a little bit better now.
Yeah. So that's how you get the size of COA, right? So so this question, I was assuming that you guys can dig out the previous slides and figure out how much it would take for each of the adder. Okay, so is Nicholas, is that okay for you now?
Yeah, it's a little bit better. Again, the thing is, I guess I don't quite understand the pipeline thing yet so far and how that kind of plays into things.
Okay, so let's see if Fox has anything to say. And if both of you guys are not clear about that, then I will follow up with that. And let's see, Fox, what do you think?
Oh, I mean, when I was looking at this problem, the obvious, well, so I mean, the first thing to identify that was most obvious, and this I felt a little cheaty. So you can figure out the answer without having to do the whole problem. At least that's what I think. The 32-bit carry ripple adder made with 32 full adders is probably the bare minimum for what you could do, because your 32-stage pipeline serial adder also requires 32 1-bit full adders. So with that baseline, we know that the 32-bit carry ripple adder is actually the smallest, which answers the question for us. But if we actually want to dig into the question, then the most obvious biggest one is going to be the 8-stage pipelined adder with the 4-bit carry look-ahead adder, because that's the 32-bit carry look-ahead adder with registers added. So then the question becomes comparing the 32-bit carry look-ahead adder with the 32-stage pipelined adder. And it comes down to whether the additional 32 registers are bigger or the additional 8 4-bit carry look-ahead modules are bigger. So, and I think the registers are bigger. I think the D flip-flops take more.
Okay, so let's take a look at that, right? So, okay, so first of all, if there is no register, right? Just the adder itself, 8 4-bit carry lookup-ahead adder, as we calculated before, the midterm is this big, right? About 2,000 transistors. And if it's a 32-bit 4 adders, making with 32 4 adders is about 1,600 transistors, right? So each of the 4 adders is 50, and for this one, you can get an approximation, like as I said, it's about 2,000, right? So, or say like it's about, yeah. So this is the this is or say like 200 or something, right? So 244, I remember. So this is the size of each unit that you will be pipelining, right? However, if you look at the design of the pipeline, right, it's actually like this. So how many, if I want to implement a 4-bit serial adder, pipeline 4-bit serial adder, I actually need 4 copies of the full adder. I actually need 4 copies of the full adder. So I need physically 4 adders. So instead of the original serial adder that you can reuse the same adder for the same job, once your job propagates to the next one, I'm done with it. I'm done with it. So you need, depending on how many bits you have, you will need this amount of adders there, right? So that's why, so if you look at this question, right? So the carry look ahead adder requires this amount of transistors, and for the carry ripple adder, this is the amount of adders you have, and this is the amount of transistors you have. And if you have a stage pipelined 32-bit serial adders made with 4-bit carry lookup adders, you have to have 8 copies of carry lookup ahead adders plus the pipeline register. So each of the adder is about 244. And for each of the pipeline transistors, let's say like, okay, we only need like 18 transistors for temperature storage. And it turns out that you will, and actually I think 18 is not the right number. You need 32 times 18 because 18 is only a D flip-flop for 1-bit data, right? So it's this big. It's this big, right? So it's 2096. And if you look at the 32 stage 32 stage serial adders, it requires 50 transistors per full adder. However, you need 32 of them and 32 of the 18 transistors. So it turns out that you will require a total of 2,200 transistors in implementing this 32 stage. So if you look at the area, the biggest is actually the fourth. And unfortunately, looks like and the land is the third, and it's actually the one and the first, right? So I was originally thinking about this way, so looks like I made it wrong. But however, this is how you get to this question, right? So this question, if you grab the point that pipeline result is pipeline require duplication of real circuits, then of each component, then you know how to solve this. It's basically like each part of the circuit, they need an additional transistor to buffer their result and times the amount of stages you have. So that's how you estimate the area and cost. And you can see like E is probably the right answer for this question if we change the direction of this greater than equal. So the cost of pipelining is actually a lot because it needs to duplicate serial units and use more area. So that's why Moore's law becomes really important. So in the past, we say about like, in the past, we can keep improving performance of our circuit because Moore's law allows us to put more transistors within a fixed area of silicon. However, just getting you more transistor within the same area doesn't make you faster. What really makes you faster is that with this more transistor, you can manage the cost of the circuit and make within a fixed area, you can put more pipeline units in there. And with this pipeline units, you can get your throughput better, improve the frequency of your performance. So pipelining need to duplicate a serial circuit and use more area. And this is why Moore's law is the most important driver for the historic CPU performance gains, because we need pipeline to implement every part of your processor, your processing, your instructions, right? So this is the why. Okay, so you learn everything. However, without this question, without giving you the concept of pipelining, it's really hard to connect them together. Why giving you more area would help you get better performance? Well, of course, the length of your wire is definitely a driving factor for that. But the real performance gain is actually coming from techniques like pipelining of this. All right, so we have finished talking about pipelining. We have finished talking about adders. And right now, let's revisit our good friend a little. So let's talk about multiplier. But before we talk about multiplier, let's talk about our good friend shifter a little bit. So so why we have to talk about this, right? Thinking about how you do this by hand. Like if I want to do binary multiplication, how do we do this by hand in decimal? So how we multiply numbers is basically like if I have these two numbers that I want to multiply together, first of all, I use the last digit of or my multiplier to multiply the multiplicand. And then I shift left by one digit and use the second one to multiply it and keep going until I use every digit in my multiplier. So that's how you do binary multiplication and decimal multiplication. And you do the same for binary in a way that, well, let's just do this and it just keeps shifting it. And so if you want to formalize it, right, if I have a two four-digit number that I want to multiply, it's basically like this. And you have practiced that in your reading quiz before, so I don't want to spend too much time on this. However, one thing that you know that if I want to achieve this kind of partial product in binary multiplication, I need to shift left. And what we just learned in the past is actually shifting right, right? So this is the circuit we have for shift right. So for the shift right, we know the implementation only require you guys to use mux and use the shift amount as the selector for your input and output. And this is the shift right, right? So right now I'm inviting you to tell me, if I want to implement shift left, how can I achieve that? All right, 15 seconds. Five, four, three, two, one. Time is up. Okay, so according to what I learned from you, a majority of you think it's C. So why don't you have someone telling me to convince that you're not just picking C because it's in the middle, but you do have thoughts about it. Okay, I have Fox. All right. Oh, I also have Xiangying. Can I have Xiangying first?
Oh, so the current implementation, you can like basically if shamped is like 0, 1, if it's like if it's input in a way that 0, 1 is selected, like 1 is selected, then it will shift to the right, and then just tag on as 0 for the leftmost bit. So we just need to, as I see, because we just change the input so that we have this like option to go the other way instead.
Okay, so Fox, do you have anything to add?
Well, I mean, can you hear me? Oh, cool.
Yeah.
The immediately obvious thing, well, I mean, we could just go through the 4 options first. We can alter the interpretation of shift amount to support left shift, maybe making it positive and negative, but that requires more circuitry. We don't need to modify a circuit, just take a nod on every input. That actually just doesn't give us the left shift at all. And we don't need to modify the circuit, just change the order of inputs. This would give you the left shift. I mean, in this case, we're implementing shift with muxes, so there's absolutely no reason why we can't implement the reverse shift with muxes as well.
Okay, so what's wrong with the A? Why can't we just alter the interpretation of shift amount to support shift left?
Well, there's no like, the problem is, of all the inputs that shift amount can be, the current circuit will shift it right no matter what. And you can't, I don't know what alter the interpretation means, but even
okay, so let's say like, okay, let's say alter the interpretation, whatever, right? So tell me one thing, in how many of the cases we are going to use A0 in shift left?
Oh, almost all of them. Actually, all of them.
Almost all of them.
All
right?
of them. All of them. Yeah.
All of them, right? But where can we find A0 in the mux?
Just the one mux on the right.
Right. So no matter how you change the interpretation of your shift amount, it's impossible for A0 to appear in all muxes.
Yes. In this configuration.
So, right. So the only thing you can do is and actually modify the circuit would help. Well, modify the order of inputs would help, right? So think about that, right? So if we make our circuit like this, like originally it's A3 to A0, but right now it's A0 to A1, right? Then what will happen is just like, this is what you want, and you just reconnect the circuit like this, and it works. You don't need to change the interpretation of shift amount, right? So Xiangying, are you okay with, is this what you are thinking?
That's similar to that, but
okay.
But yeah, it works like that. But, I thought like the way I thought about is that it can input in the same order, but we just wire it differently so it can shift to the right. Shift to the left.
But this is even easier, right? You just change the input order, right? And you are done with shift left, right? Awesome. Okay, thanks for your comment. So right now, right again, this everything is before you learned this before the midterm, but the textbook didn't give you this kind of example, right? So how to support the shift left? Actually, you just need to change the order of inputs. However, sometimes we want to shift left, sometimes we want to shift right. So how can we do this in a way that's more generic? So if you want to implement a generic shifter, right, all you need to do is that you need muxes, and we just select the input, probably like what Xiang was thinking about, is that we have different wires to the input, and we have a quotient, a select signal for those muxes saying that, okay, are we shift left or are we shift right, in a way that we can select the right input order for the following muxes to implement a generic shifter. So in this way, right, each mux is about like 2 gate delay. So this is about like 4 gate delay for a generic shifter. However, if you exactly know if you want to shift left or shift right, you can definitely having some optimization of it. All right, so that's detour back multiplier. And let's see, right? We know to accomplish a multiplication, you need to shift and add. So the very basic idea, if I want to have a 4-bit multiplier, because the result could be a bit. So the best thing to do is that we just have a couple of the bit adder. Well, you can definitely optimize this as 5, 6, 7 to further shrink the amount of circuit you have. But if you use carry lookup adder, then the 8-bit adder is actually sharing the same latency as the 5-bit. So as a simplicity here, I draw it as 8-bit. However, you can definitely make it smaller by using 5-bit, 6, and 7-bit adder, and it doesn't affect your result. And the shifter, again, right? You can make it like 5, 6, 7 to have your to shrink the size of your circuit. However, that's not the biggest point that I want to talk about here. What I really want to talk about here is that, well, so first of all, let's look at the concept of that, right? So I use B0 to select it's 0 or 1. And if 1, I am adding its original number, right? And if it's 0, then I'm just adding 0. So that's the shift and add. And shift the number by 1 bit every time you add it. Right, so that's basically how you do multiplication. So and you need to do it for 4 times, right? So because you have 4-bit, right? So and if you add this delay together, you will figure out like for each mux it takes 2, and let's say like carry lookup adder, if I'm doing it 8-bit, then it takes about 5 gate delay. And for shifter, well, if I have a generic shifter, then it's 4. And for a mux, it's 2 again. And then if you aggregate everything together, for this shift and adder, if I want to add 4-bit of multiplication, then it takes about 40 gate delays. And prior to midterm, you probably read this in a textbook that we can further optimize the adder in a way that we just like the concept of carry lookup adder. We know this is everything we want to do. And we know every number will be interacting together at least once. So let's just make an array. So this is the line for all the bits in A. And this is another direction for the B. And here, as you can see, we are doing an AND for every single digit in the multiplier. And then we connect this wires together, use adders to add their partial sums, and this is how we get a final result, right? So this is the basic concept of array style multipliers, in a way that we just make all the terms of A, I, B, J's. We add them all. We try to produce all of them together in the meantime, and then it leaves. The only thing that has to be serialized is this adders, because as you can see, this partial sum, they need to be added only after you have those results ready, right? So this is the array style adder. So I want you to think and evaluate how many gate delays we are suffering from this array style adders. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so let's see, what do you guys think? Wow, so looks like every answer is kind of popular. So can I have some of you sharing what do you think? Okay, I have Fox. Okay, what do you think?
All right, so let's solve this problem like we'd solve other problems. What is the critical path? Well, the critical path is probably going to be any path extending from the 5-bit adder, considering that's the first adder in the sequence. So it's every single input is ANDed with an opposing input. So that gets us 16 ANDs, and that gets us 1 gate delay, and then we count the gate delays of our adders. So if our adders are composed of 4-bit CLAs, then each adder is 2 4-bit CLAs. Each 4-bit CLA is about, is it 2 or 3 gate delays?
So actually, the COA unit itself is 2.
But
right?
the full adder is 1.
Right.
So that's a total of 3.
But that's 4-bit, right?
That's 4 bits, right? And then we have another carry look ahead adder. I can only assume, although for the 5-bit adder, we don't need the carry look ahead because we just have the.
No, because you are actually adding 2 5-bit numbers, so you still need a carry look ahead because you are actually generating the result for 6 bits.
Right. Yeah. Okay. All right. So then that's going to be 6 gate delays per adder. That doesn't seem right.
I would say 5. I would say 5.
5 gate
right?
delays
Because
per
you
adder.
because you have 2 carry look ahead adder, right? And generating the input for the carry look ahead unit or generating the SI for the adder is about 1 delay, or they can be in parallel. So it doesn't matter, right? But the part that cannot be parallel is actually 1 gate delay. So it's 5 for each, right? Are we done? So then you can see the answer would be which one? So the answer would be 16, right? So that's the gate delay for array cell multipliers. And if you remember what's the gate delay we just got from our shift and add, it's actually 40, right? So array style multipliers, it use more gates again. However, the performance is a lot better. But how about we have 32-bit array style multiplier? So if I have a 30, so right now I'm just doing it in 4-bit, but what if I grow it up to 32-bit? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looks like both B and C, they are kind of popular. Can I have someone explaining what do you think? Okay, I have Xiangying. What do you think?
I chose B because could get one gate delay from the just multiplying and then adding part. We're gonna have basically gonna have to have like basically 31 sets of additions and 5 gate delays each, so that will cost about 150 something.
Okay, so let me ask you this question, right? So this is the 4-bit array style multiplier, right? How do you expect the 32-bit array style multiplier looks like?
So we have like A0 to A31 and then B0 to
So
B31.
I would have 32 of this, right?
Yeah.
And I would have 32 of this, right?
Yeah.
So because you have 32 outputs here, is this 5-bit adder sufficient?
No, it'll be no, you need more than that.
Then you will be what? Okay,
like,
Fox, what do you have anything that you want to add?
It's like
oh well, I was gonna walk through the problem.
Okay, that's fine. Okay, so I will walk through that. Thanks. Okay, so how many bit adder do we need here?
We start from 33-bit.
33-bit, right? Okay, and then 34, right? 35, right? Okay, knowing this, is that going to change your mind? Are you going to change your mind? Are you still insist?
Oh, actually, yeah, I see the problem. Yeah,
okay.
Because wait, yeah, we're getting like 17 gate delays to start with. Yeah.
Right. So you have 32 to 32 here, right? And here you start with 33-bit until you reach 64-bit adders, right? And each of them is a 4-bit carry lookup header, right? So if you have this carry lookup header for 33 to 36-bit carry lookup header, this is the gate delays, right? Yeah. And they are in serial. So if you keep aggregating them, right, what you end up with is something greater than 1600. Fox, is this also what you think about?
Hold on, I put down the wrong answer initially because I did my math wrong. Right, we need we need 33 64-bit adders.
33 to 64-bit.
Oh, gotcha. Yeah, so that's going to be. So you're calculating the gate delays. How many gate delays is it per 4-bit CLA?
It's actually gate delay per 4-bit is actually 2, right? It's always 2 times something plus 1. Right?
Okay, so what's the?
I think we're ignoring the +1 because they won't.
I'm looking at like let's say for the first line 33 through 36 bit adders is 4 times 9 gate delays times 4. I'm lost on where the math is on that.
Okay, so I guess this part is probably so for the 33, right? We need 9 COA unit, right? And each of them, okay, so each of them is 2, right? So 2 times and each of them is 2 and plus 1. So that would be okay, so I got this wrong, right? So this is actually not this is actually I'm saying this is actually 19 times 4, right? So I will modify this number later,
And they
Okay,
should increase
but
like
thi-
2.
All right, because that changes the answer.
right. But the thing is that this is the concept, right?
Right.
Okay, so we are running out of time. So let's get back to this question in the next week, and I will give you, I'll publish the right answer on the slide. But this question still give you an idea, like what are we going to ask in the final? Is that we are going to connect everything together. So you learn this concept in a textbook. However, textbook doesn't really give you real examples. And for digital design, what you really want is real examples. So
Hey.
I will. Yes.
I actually have a quick question. Something that's been bothering me about this course for a while now is I actually can't, for the life of me, figure out how we're supposed to count gate delays, because at different parts of the course and in different parts of the textbook, we've counted them different ways. And
really?
Yeah, so it'd be
because
like
the textbook, I think well, so first of all, right? So the textbook only say that, well, if you have like one gate is a 1 gate delay. Right.
Right. Like multi-input gates still have the same delay.
Yes.
But that's a simplification we didn't do at the beginning of the course. I've been confused. I'm just saying.
We have been doing this for a while.
Well, yes, I'm just saying when we first covered gates as CMOS, that at the very beginning of the course it was slightly different. I mean,
yeah, but this is a simplification, and I did mention that when I introduced this one. I say, well, we have different methodology, but this is the default way that we are doing in the class.
All right, it would be nice, I think, if you could at least put out some kind of a reference sheet for how we count gate delays, just as a thing that I can and the other students can refer to count gate delays.
No, because for the textbook, it always say that, no matter what gate it is, right? It's always the same delay.
Right. I'm just how to count the gate delays of say the carry look ahead adder, because obviously there has been some inconsistency at some point.
No, I think we are pretty consistent.
All right.
All right. So, well, before you leave the lecture, a few things. Left 5 due to 9. Left 6 is up. Office hours that we all share the same meeting instance. Find out your email regarding what's the right link of joining us. And that's reading for next Tuesday. Check your grade.
What the fuck, say?